18. So today I'm going to go through some math stuff for you. So this will be the mathematics that we need for inductors and capacitors in Module 5 Electricity Systems. Inductors and capacitors in AC circuits. So topic number, whatever, 12, something like that. The second to last topic, Module 5. If you haven't watched the lecture video yet, please go and do that. So that's where I've gone through the PowerPoint presentation. You'll need to have a quick look at that first. I haven't covered this stuff in detail, but just talking through some of the concepts going through our PowerPoint. This is aimed specifically at the maths. Now, when you do the test for this is pretty much what you're going to get. So I thought I would do a couple of examples of the kind of maths that you're going to see in the test. I will also make available, I haven't figured out quite the format yet, but I will make available some practical examples for you, some practice stuff for you to do. So watch this, follow along with me if you can, get your calculator out, even pencil and paper, write down what I'm doing. That can be your first couple of practices, and then go on to do the practices on your own. Get in touch with me, please. If you're struggling, please get in touch with me. Doing this kind of test, this kind of teaching remotely is difficult. I think it's going to be difficult. So if you're struggling, please get in touch. I don't expect everyone to just understand this stuff straight off the bat. Okay, so let's start at the start, and let's get rid of my face. Make life a bit easier. There we go. So here's our problem. We have a circuit here that has a resistor, an inductor, and a capacitor. Please forgive my poor drawing. So we have a series circuit with a resistor, an inductor, and a capacitor. And we're given a bunch of values here. So we're given the frequency, 65 Hertz. We've been given the resistance, so that's the resistance of this resistor, as 38 ohms. The inductance, so that's the inductance in that coil there. Note that this is not the inductive reactance, it's just the inductance. So that's a value in henries. We've been given that as 122 millihenries. And remember, just make note of the millihenries there. When we put that into our formulas later, we're going to have to remember that that's in millihenries, so we need to convert it. The value of the capacitor here, capacitance of that capacitor is 35 microfarads. Again, that's something that we will have to convert. And our supply voltage we've been given here, 240 volts. So we've asked a series of questions. Apologies again for my sloppy note taking. I got the numbering wrong, but you can just ignore that. So it's asking us to find first capacitive reactance, second inductive reactance, third total impedance, fourth the supply current, so that's how much current is flowing through the circuit. 5 will be 3 parts, the voltage across the resistor, the inductor, and the capacitor. 6 is the phase angle. What's the phase angle? So is our current leading or lagging the voltage, and if so, by how much? And our power factor, so the efficiency of it. If you're a little bit sketchy on power factor, don't worry. The next module talks more about power factor. So let's call it efficiency for now. I know that in the lecture video for this topic there's a little bit about power factor. It's not a huge amount, but let's say it's a measure of efficiency. Remember, it's true power divided by apparent power. So it's how much power I can use versus how much power I'm paying for. That's really what it comes down to, power factor. But for now, as long as we understand the maths around it, then we don't need to worry too much about what that power factor is. So our first example here, the first question rather, capacitive reactance. I need to find capacitive reactance. What's my formula for capacitive reactance? 1 over 2 pi FC. 2 times pi times frequency times capacitance. and that gives me my capacitive reactance. So my capacitance is the value of capacitance of the capacitor. Capacitive reactance is the resistance to current flow of that capacitor. So if I substitute in my values from the top here, I'm going to need frequency 65 and capacitance 35 microfarads. So I go 1 over 2 pi times 65, that's my frequency, times 35 times 10 to the negative 6. So it's 35 microfarads. Remember, if we want to convert from micro back to regular units, so from microfarads to farads, we multiply that by 10 to the negative 6. Experiment with that in your calculator. Make sure that you can get the right answer. What you need to do is figure out where the brackets go, essentially. When I'm doing this, I'm putting a bracket here in front of the 2. I'm putting brackets around the 35 times 10 to the negative 6, but actually you might not need those, and then another closed bracket here. And then the result I'm getting is 69.96 ohms. Question number 2 was inductive reactance. Now the formula is more or less the same, except I'm not doing the 1 over, so it's 2 pi times 2 pi FL, 2 times pi times frequency times inductance. Obviously XL is inductive reactance, so L will be inductance, not capacitance. 2 times pi times 65, so our frequency is the same as in the last question, and our inductance is 0.122 henries. Again, if we look up here, inductance says 122 millihenries, so I'm just converting that myself, from milli to millihenries to henries is just a matter of turning that 122 into 0.122. If you are not confident with that or don't understand what I did, then you need to multiply your 122 by 10 to the negative 3 to go from millis back to regular numbers. We multiply by 10 to the negative 3, and that gives me an answer of 49.83. That is my inductive reactance for this one. Question number 3 was total impedance. Look at question number 3, total impedance. Well, what do I need to know to get total impedance? Well, total impedance is going to be adding up of our resistance. So we need our resistance, inductive reactance, and capacitive reactance. Now remember that our inductive and capacitive reactances are opposite to each other, so they will subtract from each other, and that's the vertical axis of our triangle. The resistance is the horizontal side of our triangle. So what I need to do is turn that XL, XC, and resistance into one triangle, and then the hypotenuse of that triangle is my impedance. So if I just zoom out of there, let's have a look here. I've drawn a triangle here for you. So this is not necessary, it's not part of the requirement of the question. However, it's going to make our lives a little bit easier. So where are we? Yeah. So I've drawn on vertically here, that's my inductive reactance. Down here is my capacitive reactance, and here is the horizontal there is my resistance. So you can see that if I subtract these two, the inductive reactance and the capacitive reactance, I'm left with this component here. So that's the sum of my two reactances, and then that means that this line here that joins the resistance and the total reactance, that's my hypotenuse, that's going to be my impedance. So if we come back to this one, you can see that I've done that there by going total reactance equals XL minus XC. So 69.96 minus 49.83 equals 20.13 ohms. So that 21.13 ohms, that's this line here. The vertical line that is left after I've subtracted the capacitance and inductance, or capacitive reactance and inductive reactance. So then I use that. Now if you go back to the previous video, the lecture series, the lecture video for this topic, you'll see that we had a few different formulas for total impedance, and we could do this XL minus XC inside our impedance formula, but I find it easier to do it outside, so I'm going to go XL minus XC first to get my 20.13. And then all I'm doing is working out the hypotenuse of that triangle that's formed by the reactance, X, and resistance, R. So like any right angle triangle, I can use the Pythagoras theorem to find my hypotenuse. I go square root, so that's my impedance, that's the hypotenuse, square root of X squared, so that's my reactance squared, plus resistance squared. My reactance, total reactance, remember, was XL minus XC, so total reactance is 20.13, so I square that, and I add 38 squared. If we look back to the top, we'll see that our resistance, the resistance of that resistor, is 38 ohms. So the square root of those two squares added together is 43 ohms. Nice and round number there. So that is my total impedance, is going to be 43 ohms. Next question, number 4, was find the supply current. So what do I want to do to find the supply current? Well, I've got a supply voltage, right, and I've been given that was 240 volts. I now know my total impedance of the circuit. So that 43 ohms that we worked out in the last question is the sum of those three impedances. Remember, when we say the sum, when I say the sum of those impedances, I don't just mean adding them all together. What I mean is using those formulas to give us that correct value. So the sum of those three impedances, the resistance there, the inductive reactance, and the capacitive reactance, that equals my total impedance. So I can work out my total current by saying I equals V over R. That's just Ohm's law, right? Current equals voltage divided by resistance. In this case, for resistance, we're actually talking about impedance, so that could be a Z. So that equals voltage over total impedance, which is 240 divided by 43. So we got the 43 up here from the previous question, total impedance, which gives me a value of 5.58 amps as my total current. It's my supply current. Now in a series circuit, current is going to be the same at every point. So if I measure the current here, the input current, 5.58. If I measure the current in that resistor, 5.58. I measure it in the inductor, same. Capacitor, same. On the output, same. 5.58 amps everywhere on that circuit. So if I go into question 5 then, question 5 was, what's the voltage present across each of those devices, or what's the volt drop? Now this is where things get a bit sticky, because normally we would add our volt drops together and that equals our total voltage, but we know that in these types of circuits that's not true. But we can work out what the individual volt drop is at each component, and we do that with our simple as Ohm's law, V equals IR. So the voltage at any given point, the voltage across a given point is the current that's flowing through that times the resistance of that component. And in this case we'll use resistance. If it's the resistor, we can use we will use inductive reactance. For the inductor, we will use the capacitive reactance, whatever the resistive component is of that particular item. That's what our R will be. So in the first one, 5.58, that's my current. Remember, current will be the same everywhere in the circuit. Multiplied by 38 ohms, because it's the resistor, gives me 212.07 volts. The voltage across the inductor will be, is it the inductor? Yes. Current again, 5.58 times 49.83. That's my inductive reactance from earlier. My inductive reactance is 49.83, so I times R equals 278.07. And then looking at the capacitor, again 5.58, 69.96. If we go back up here, we'll see that's my capacitive reactance from the very first question, 69.96. So 5.58 times 69.96 equals 390.43 volts. Interestingly, and you'll see this in the next question because I've set it up specifically for that, you'll see that that voltage across the capacitor is significantly higher than in the supply voltage. That is, the physics of that probably more complicated than I can explain. Maybe more complicated than I even understand. What we can say about that is one of the reasons why power factor correction and these kind of RLC circuits can get a bit dicey is because we start to see some really high voltages present in these circuits that perhaps are unexpected, right? Because it's significantly higher than the actual input voltage. Right, so those three, so we've got A, B, C, 5A, 5B, 5C there, those are the voltages across each of those components. And trust me, it might sound crazy, but if we built a circuit like this and we put a voltmeter across those components, those are the volts that we will get, I promise you. Maybe one day we'll do that. I'll build a circuit like this and measure those voltages, see if we can get a voltage that's higher than the input. Question 6 was the phase angle. So are we leading or lagging? And what is the angle? So I've written here, I've got using resistance and using power, because there's actually a couple of ways that we can do this. If we look back at this triangle here, you see that that I've written for each component. So this is the inductor here. I've got inductive reactance, voltage on inductor, which we just worked out, power on inductor, which is V times I. So using the 5.58 from earlier, that gives me the reactive power of the inductor. For the black line here, I've got resistance 38, voltage on resistor 212, true power, because our resistive power is our true power, V times I equals 1183. Here I've got total reactance, so that's the inductive and capacitive components. In red, I've got the values for the capacitor, and at the bottom I've got the total value, so total impedance, total voltage, and apparent power. That's my apparent power there, the hypotenuse of that triangle. What you'll notice about that, if you start to look at those values, is actually, even though if I drew this triangle, if I drew these three lines and then that triangle, and I used the resistance values, inductive reactance, resistance, capacitive reactance, total impedance, the triangle looks exactly like that. If I went and used the voltage on the inductor, voltage on the resistor, so on and so on, and I drew them all, they're different values, but the triangle looks exactly the same. If I used power on the inductor, true power, that's the resistive power, reactive power, that's this power here, the combination of XL and XC, or power on the inductor and power on the capacitor, which would be opposite, so they cancel each other out. I'll subtract one from the other. And I use total power, the apparent power rather, that's on this one here. Again, those values are different, right? 1339, 2178, so on and so on. But if I plotted all those values for power and drew the triangle was the same, because all of those values are related to each other. So I could use any of those values to work out what my power factor is. So I've gone with a couple here. What I'm using is, let me back down to question 7. What I'm using is either resistance or power. So to find that value of that angle, this is just trigonometry, and you'll need to look back at your trigonometry if you can't remember this, but to find the angle, if I use cos, I'm going to use cos in this example. So cos, remember car, soc car toa, so C-A-H, cos adjacent hypotenuse. So cos to the -1, so inverse cos times adjacent over hypotenuse is my angle. Remember, I use the inverse cos because I'm trying to find the angle. Normally we would use cos of the angle times one of the other sides to find the value of a third side, or a third value. In this case, cos to the -1 times adjacent over hypotenuse equals 38 over 43. So that's my 38 is the resistance, 43 is my hypotenuse. Let's just have another look at where I've got those values from. 38 is the resistance here, so that's that horizontal side of this triangle. 43 is my hypotenuse, so I've worked that out earlier. That's our total impedance, right? 43 ohms across there. So if we're using inverse cos of that side and that side to give us the value of this angle here. That's my phase angle, the angle between those two lines. So when I do that, it gives me a value of 27.91 degrees. Now I've also done it using power, so exactly the same formula, cos to the -1 times A over H, but in this case the adjacent I've used the resistive power, true power, and the hypotenuse I've used apparent power, so that's the total power, total input power, total power that we're paying for. So if you go back, if you have a look at that triangle, you'll see that this is the horizontal component, that is my hypotenuse, so the ratio should be exactly the same. 38 over 43 should be the same as 1183 over 1339, and therefore if I use those, substitute in these values into the same formula, I should get the same result. And I do. You'll see here that cos negative, the inverse cos to the negative 1 times 1183 over 1339 rather, is 27.93. Very small difference there, that's just rounding because I've rounded those numbers, but I've got the same angle, so you can see that the triangles are the same, and therefore the angles will be the same. Even though the values are different, the triangles will look the same. Then the last question asks us to calculate the power factor. Well, that's pretty easy because we're already actually done it. The power factor is just the ratio of true power to apparent power, so it's going to be true power divided by apparent power, which would be 1183 divided by 1339 equals 0.88. So we would say a power factor of 0.88. Or another way of doing it, because now we're just doing the reverse of this one here. So if I go cos of the angle, then that will give me 1183 over 1339, because I went inverse cos of that fraction gave me the angle. So if I go cos of the angle, it'll give me that fraction, which is 0.88. So I've got it two ways. 0.88. Doesn't make perfect sense? I hope so. Let's move on. I've got another example that's exactly the same. If it wants to, there we go. Okay, so in this example, looks like I've chopped the top of my R off there. This is exactly the same. We've just got some different values. So again, we've got a series circuit here with a resistor, a inductor, and a capacitor. Voltage input 235 volts, and our values are given 40 hertz frequency. 10 ohms is the resistance of that resistor. The inductance in the inductor is 125 millihenries. Again, remember that's millihenries, so we have to convert that when we use that in our formulas. Capacitance is 150 microfarads and voltage 235. It's asking us to find the exact same things: capacitive reactance, inductive reactance, total impedance, supply current, voltage across each of the components, phase angle, and power factor. Again, if you can follow along with me on your calculators, maybe write this out as you go. That's going to make your life quite a bit easier when you come to do these examples yourself. First question, find the capacitive reactance. XC equals 1 over 2 pi FC. Substitute in the values that we know. Our F frequency was 40 hertz, and our C capacitance 150 microfarads, so that's 150 times 10 to the negative 6. Remember, I've got to convert my micros back to farads. 150 times 10 to the negative 6 equals 26.53 ohms. Question number 2 was find the inductive reactance. So XL, that's my inductive reactance, equals 2 pi FL. 2 times pi times 40, that's my frequency, remember 40 hertz, times 0.125. Again, I've just converted that millihenries back into henries. I've done that just by changing the decimal place. If you're confused by that or it doesn't make sense, use 10 to the negative 3. So it would be 125 times 10 to the negative 3. Work that formula out and we get 31.42 ohms. Next question, find the total impedance. Well, before I find the total impedance, again, I could use the formula with the XL minus XC in the formula for impedance, but I like to do it outside it. So I find my total reactance first, which will be XL minus XC. So I've got 31.42 minus 26.53 gives me 4.89 ohms. Notice that that's a pretty low number. My XL and my XC are pretty close together, which means this is pretty low, and that will lead us to some interesting values later on. Then I go into impedance, right? So Z, remember this is just my Pythagoras triangle. If we remember that last question where I had the triangles, and here's the triangle for this one. I've got, this is the impedance. Sorry, that's the inductive reactance, this top line. The red line is the capacitive reactance, black line is the resistance. So once I've subtracted the inductive reactance and the capacitive reactance, this is what I'm left with here. And so when I'm working out my impedance, what I'm doing is just working out the hypotenuse of the triangle between the resistance and the combination of my two reactances, which is that 4.89 ohms here. So I substitute into this formula here, Z equals X squared, that's reactance squared plus resistance squared. It's square root of X squared plus R squared. So I put a square root of 4.89 squared plus 10 squared. So I haven't put the square on there, my mistake. I've missed out a little square, but that should be squared there. So 4.89 squared plus 10 squared equals 11.13 ohms. That's my total impedance. Next question was number 4, find the supply current. Very simple, I equals V over R. In this case, we're going to use total input voltage and total impedance. So we have here total voltage, total impedance, which equals 235. That was given value here for input voltage. 235 over 11.13, which is our total impedance from the previous question. Gives us a total current of 21.11 amps. Question 5 was find the voltage across each component. Again, this is a simple case of V equals IR, basic Ohm's law. So I substitute in my current, 21.11. The current's going to be the same at every point. And the resistance of that component, in this case the first one, 5A, was resistor. So we have 10 ohms on the resistor, 21.11 times 10, 211.11. I'm going to use the same current for B, which was my capacitive reactance. No, it's going to be the voltage across the inductor. B is 21.11 times 31.42, which was my inductive reactance, right? So that's I times R, V equals IR, gives me 663.22. And at the capacitor, 21.11 amps times 26.53 ohms, that's my capacitive reactance, equals 559.99. In the previous video, when the PowerPoint for this topic, one of the things that talked about saying that we don't want to use unity power factor is because of the possibility of unstable voltage or voltage spikes. And that's what we see here. Even though we've only got 235 volts on the input, you can see on that inductor, we're now at 663 volts. And that's 663 real volts, so that's going to present a hazard to our insulation, because high voltage breaks down insulation, and potentially to us, to people, right? 663 volts is a big number. So the next question was the phase angle. Again, for phase angle, I've gone through. If you have a look, you can pause the video if you like and examine the numbers that I've put in here. I'll find a way to make this make these pictures available to you as well, so you can use them. But you see that again, the ratios of that triangle are the same regardless of whether I'm using reactance, resistance, impedance, or voltages or power. So reactive power, true power, and apparent power. Either way, the triangle looks the same, and therefore the angle should be the same. So I can use different formulas to do that. And here we have it here, using resistance, cos, or inverse cos to the -1 times adjacent over hypotenuse equals 10 divided by, or adjacent over hypotenuse is 10 over 11.13, 10 being my resistance, that's my adjacent in this example, and the hypotenuse being the total impedance, 11.13, gives me 26.06 degrees. If I use power, then I'll go cos to the -1, inverse cos times adjacent over hypotenuse. Adjacent over hypotenuse in this case will be true power divided by apparent power, which will be 4456.32 divided by 4959.89. If you're confused about where I got those power numbers from, remember power is just volts times amps, right? So I could use the voltage across each of those components, and here I have those voltages here, 1, 2, 3. Use the voltage across each of those components times the current will equal the power. Apparent power, total power, will be total voltage times total current. Resistive power is going to be the voltage on the resistor times the current. So 4456.32 is 211.11 times 21.11, that's our current. So if I, by using that example there, by using power instead of resistance, if I work that out, so inverse cos of 4456.32 divided by 4959.89 gives me 26.04. So very little difference. Again, it'll just come down to rounding. 26.06 or 26.04. You could use either of those. And the last question, number 7, was power factor. And power factor is a simple ratio of true power, that's usable power, divided by apparent power, the power that I have to pay for. That's just a calculation for efficiency, right? Basically input versus output. True power is the power I use, apparent power is the power I pay for. So 4456.32 divided by 4959.89, same as what we had over here. True power divided by apparent power equals 0.9. Or I can just reverse this equation that I already did, because if I've gone inverse cosine of true power over apparent power equals 26.04, then cosine of 26.04 will equal true power over apparent power, which is my formula for power factor, and that gives me 0.9 as well. That's it. Okay, next step for you from here is to, there you are. Next step from here is to do the practical examples. I'm going to set a couple of examples that look exactly like that with different values, and I need you to go through and do those. I'm going to set those up rather than doing it on a piece of paper. What I'm going to do is set those up online. I've got a couple of options. Obviously when I send them to you, then you'll know what they are. I need to figure out how to do it, but the advantage of doing it online is that you'll be able to put those answers in and then find out whether you got them right or not, rather than writing it all down on a piece of paper and then expecting me to look at that. You'll be able to enter your answers online, and you should be able to get some immediate feedback on whether you got it right or not. Again, if you're struggling, need any help, please let me know. Here to help you. That's it from me. Thanks, Steve.